So now I'm going to hand it on to Alex and Lau. It's loading. Well, first, to introduce ourselves, my name is Vineet Rao, and I'm a current junior at Prospect High School.
My name is Ambardekar, and I'm a current junior at Green Hope High School.
My name is Alexander Lowe, and I'm a current junior at Mission San Jose High School.
My name is Sanjay Ravishankar, and I'm a current sophomore at Amador Valley High School.
And we're missing one guy, Christopher Lau, and he is a junior at Mission San Jose High School. So now I'm going to hand it over to Alex.
Hello, everyone. Today we will be presenting the analysis of stellar attributes to determine the feasibility of carbon-based life in exoplanets.
So as a brief intro, the first exoplanet was discovered in 1992. And ever since then, over 5,000 confirmed exoplanets have been prominent in the solar system, or at least been discovered. And finding habitable exoplanets can give us deep insight into the early history of our solar system and how primitive lives have developed over the course of many years. And this is crucial to determining any other research areas, such as biological systems and the chemical compounds that are responsible for constructing human life. And we determine habitable exoplanets through our own methods, and we call it the circumstellar habitable zone, or CHZ, within their host stars. If an exoplanet's average orbiting distance was within the bounds of the CHZ, then we deem it to be habitable. And if it's in the outer bound, it means that it's the outer Goldilocks zone. If it's in the inner bounds, that means it is at the minimum value for it to be deemed as a habitable exoplanet. And thus, we found out that exoplanets would have low eccentricities and their host stars would have relatively low surface temperatures, which in theory makes a lot of sense because a low eccentricity means that it can radiate light a lot better to further have human life on exoplanets. And these would both increase the chances of habitability. And now I'm going to hand it on to Chris, who will explain a bit more about this.
Chris, you're unmuted. You're muted if you're trying to talk.
Oh, sorry. So the overarching purpose behind our search for exoplanets was to reveal the possibilities of life beyond Earth. Ever since the first exoplanet was confirmed in 1992, there have been over 5,000 confirmed planets outside our solar system. During the hunt for potentially habitable exoplanets, we determined that while little information is known about the abundance of carbon on an exoplanet, the most vital factor in determining carbon-based life in the celestial body is its ability to sustain liquid water. Our primary method for determining an exoplanet's habitability and ability to host liquid water was to determine the circumstellar habitable zone, or CHZ, of its host star, or the range of orbits around a star in which an exoplanet can support liquid water. You can see a rough estimate of what a star CHZ would look like in the lower right image. And as Vineet said, if the exoplanet's average orbiting distance was within its host star CHZ bounds, we deemed the planet to be habitable. So we hypothesized that the exoplanets we found to be habitable would have overall low eccentricities, and their host stars would have surface temperatures less than or equal to 7,500 Kelvin, the upper limit for the temperature of an F-type star. Although the majority of the 60 exoplanets that we deemed to be habitable agreed with our hypothesis, there were a few exceptions, which shows that exoplanets that have conditions that are traditionally thought to be unfavorable to suit life can still potentially be habitable. The now defunct Kepler Space Telescope, which has helped to discover and gather data from many of the planets in the Exoplanet Archive, can be seen in the lower left image.
Next slide. So the main source of data that we used during our research was the NASA Exoplanet Archive, which is a database that contains over 30,000 entries of exoplanets. However, before using this dataset, we needed to filter it to ensure that we had the most accurate data possible. Our first step was to remove exoplanets with a controversial flag. A controversial flag of 1 meant that the exoplanet existence was questioned in the past, and thus its data was relatively unreliable. but a controversial flag of 0 meant that the exoplanet was a confirmed exoplanet, making it a potential contender for being habitable. We thus used a Python program to remove all exoplanets that had a controversial flag of 1. The next step was to remove all duplicate values in the NASA Exoplanet Archive. As of August 2022, as mentioned, the dataset has over 30,000 entries, but this is including multiple entries of the same exoplanet. To eliminate the duplicate entries, we first arranged all of the entries in ascending order based on publication date, so oldest to most recent. Afterwards, we intended on only keeping the last occurrence of a particular exoplanet with multiple entries, because the last occurrence would correspond to the entry with the most recent publication date, since it's ordered from oldest to most recent. And the most recent entry would have the most accurate information about the exoplanet. So the image below shows an example of how our code works. The exoplanet 14 Hercules B had 7 entries in the original dataset, but after applying our deduplication algorithm, there was only 1 entry for the exoplanet, and that was the one with the most recent publication date.
So our next method was CHC, which, as mentioned earlier, is a circumstellar habitable zone. So our first step within the CHC was determining the standard luminosity and absolute magnitude of a host star for each exoplanet. And this standard luminosity can also be referred to as the stellar luminosity. And then we would further use the bolometric correction to find bolometric magnitude and luminosity for each host star specified. And it can be inferred that the bolometric correction varies between each planet with different luminosities and different host stars. And at that point, we were further able to determine and scrutinize the inner and outer bounds of the CHC for each host star. And as mentioned earlier, the inner bound of the CHC was like the lowest possible value, and the outer bound is the highest value by which the Goldilocks zone can exist within an exoplanet. If the orbit of an exoplanet lied within its CHC, meaning that it seemed to be habitable, we put it within our potential contenders for planetary habitability, which means that it can sustain carbon-based life. And thus, our last step was outputting a data set taking the habitability status of each exoplanet, by which we determined roughly 60 exoplanets in common. And below on the right, you can see that these are equations that we used by which we determined the bolometric correction and the inner and outer bounds of the CHC. On the top right is a Stefan-Boltzmann law, which we use for the standard luminosity, and the bottom right equation is the equation we used for finding the absolute magnitude. And so in terms of our results, we found 48 exoplanets that had a controversial flag of 1. And out of all that data, 84.5% was removed via deduplication code. And thus, we were successful in removing a lot of unnecessary entries as a result of our CHC code. And it's worth saying that our deduplication code helped remove roughly the largest portion of the entries, narrowing it down to just over 5,000 exoplanets. And as mentioned earlier, we found 6 exoplanets to be particularly habitable, with 3 in common with the PHL dataset. And roughly 2,500 planets were deemed not habitable, where exoplanets had low eccentricities, a small semi-major axis, and host stars with low surface temperature, which again can relate because low surface temperatures means that a planet's eccentricity lies within the zone that can sustain carbon-based life. And the diagrams on the left and right can visually interpret the amount of duplicates we had and the amount of planets that were considered to be within SHC.
The process that we used, the CHC process, was limited in the sense that it could not be used for approximately 2,000 entries in the dataset. This was because the planets that we checked were not in planetary systems in which the host star's stellar luminosity could not be calculated. Since the stellar luminosity is necessary in the CHZ process, these planets were not included in our research. Additionally, the deduplication code was also limiting our research. The code only took the most recent values for each planet in the dataset. While this may seem good, as we're using updated data, it could also backfire if the most recent update had missing values for some columns. If an exoplanet had too many missing values in the most recent update, as seen in the image, we would not have any values for those columns, even if the previous entries had no missing values. This limits our research because we could potentially miss some important values that had been present in earlier updates. Overall, our research was limited both through the CHZ process and the deduplication code.